Hello, my name is Giorgio Morales. I'm a second year PhD student in computer science at Montana State University and a current member of the Numerical Intelligence Systems Laboratory. I received my Bachelor in Science degree in Mechatronics Engineering from National University of Engineering in Lima, Peru. My research interests are deep learning, computer vision, and precision agriculture. And today I'm going to present our paper, Hyperspectral Band Selection for Multispectral Image Classification with Convolutional Networks. Before I start talking about hyperspectral band selection, we need to understand what is a hyperspectral imaging system. It is a system that can capture contiguous spectral bands to form data cubes. The difference with respect to the normal cameras that have only three channels, red, green, and blue, is that these systems capture hundreds of spectral bands. That means that for each pixel, we have a lot of information that comes from different regions of the spectrum of light. These systems are widely used for remote sensing, for example, for agriculture applications, like in this case, where we want to differentiate between different crop types. They are also used for food quality or biomedicine applications. So the motivation is that we observe that dealing with these images is challenging due to the increased volume of data. We also observe that the fine spectral resolution is not always needed. It can introduce redundancy in our data, which is a problem for many machine learning models. So we should prioritize the computational efficiency when storing and processing the data. For this work, it is relevant to compare multispectral imagers and hyperspectral imagers because the first ones are simpler. They can handle up to 10 spectral bands, but hyperspectral imagers can gather much more detailed information, which raises the question if we can get similar classification performance from multispectral imagers if we select just a reduced subset of salient wavelengths from hyperspectral imagers for a given application. The contribution of our work is the proposal of a future selection method to identify the most relevant spectral bands given a hyperspectral image classification problem. Our method has two steps. The first one is called interband redundancy analysis. It groups similar spectral bands and reduces the search space dramatically. The second step is a wrapper-based method called greedy spectral selection, which takes the bands that were pre-selected by the previous step and selects the best K candidate bands based on entropy and degree of multicollinearity. It is worth noting that in our case, K is a design specification that depends on the maximum number of bands that a system can handle depending on the specific application. In this work, we are using two hyperspectral datasets. The first one is the Kocha dataset. It contains images of the wheat Kocha, and we have three classes of it. The first one is resistant to the glyphosate component of some herbicides. The second one is resistant to the dicamba component, and the third one is susceptible to any kind of herbicide. These differences cannot be seen in color images. That's why we need to use multispectral or hyperspectral images. The second dataset is Indian pines. It is an aerial image that contains 16 classes, among agriculture, forest, and other kinds of vegetation. Now we can start talking about the first step of our method, the interband redundancy analysis. We will take the whole spectrum and we will divide it into groups of similar spectral bands. Then we will select only one representative band from each cluster. After doing this, we have reduced the redundancy and we have reduced the total number of bands without losing significant information. We do this by iteratively calculating the variance inflation factor between pairs of bands in order to determine how correlated they are. The BAF value between two bands is calculated based on the R-squared value that comes from an OLS regression model. So if the BAF value between two bands is greater than a given threshold, we say that these bands are correlated because you can explain one of them based on the other. And the literature tells us that a common threshold is 5 or 10. So what we're going to do is to try a range of values between 5 and 12, and we will select the BAF threshold that gives us the best separability of classes. And this is how the method works. We have n spectral bands in total. Here we are analyzing the band X4. First, we compare it to its left neighbor, and we calculate the BAF value. Here, it turns out that this BAF value is greater than a given threshold, which means that these bands are similar. We compare the next neighbor, and again, these bands are similar. And we stopped when analyzing the next neighbor because the BAF value is less than the threshold. So we set the value of the variable d left for x4 to 3. This value represents the number of bands and we need to move away from X4 in the left direction in order to find sufficiently different information. We repeat this process for the right side and we find that d right is equal to 3 as well. So all the bands that are here are similar, and that means that they belong to the same cluster. We notice that X4 is a good candidate to be a cluster center because it is similar both to the left side and to the right side. If we repeat this process for X5, even though we find the same cluster, we notice that it is not a good candidate to be a cluster center because the absolute difference between the left and the right is greater than in the previous case. So we will store the absolute differences between the left and the right for all the bands in our spectrum, and we will plot them in a graph like this. Here we have three graphs because we're using three threshold values, but in the three cases, we are getting the same behavior. So we obtain a sequence of these B structures, and we consider that the band that is at the center of this B structure represents a cluster center. For example, the band 105 represents the center of the cluster that is composed of all the bands of this region that have a similar reflectance value. So we will throw away all the bands that are not cluster centers, and instead of using 150 bands in this case, we we retain only 17 or 15 cases in this specific case. So the next step is the grid spectral selection. Originally, we had n spectral bands. We reduced it to n prime candidates after using interband redundancy analysis. But now we want to select the best combination of k bands. So the first step is to rank each candidate band according to some criterion. We chose to use the information entropy, which is defined as this. So now I'm going to use an example to explain the algorithm. Here I'm showing the indexes of the bands that were pre-selected by the interband redundancy analysis, and here I'm plotting the information entropy values of each band. In this case, I want to select only 6 spectral bands. So I select the top six bands according to the information entropy criterion, and I will use this selection to train a classifier. Here I'm showing the average F1 score after using cross-validation. And after doing this, I find the band with the greatest BIF value, which is 87 in this case. This means that this band can be easily explained by the other 5 bands. So that represents a risk of multicollinearity. I will remove this band from my selection and I will use the next available option, which is this one, 43. With this new selection, I train a new classifier, I update the F1 score, I find the band with the greatest BIF value, and again, I remove it from my selection and I consider the next available option. And I will keep doing that. Here, notice that the BIF values are getting smaller, which means that the method is considering more diverse options each time. Here, we obtain the best F1 score so far, which means that this is the best selection. And in the next step, we stop because we find a significant drop in performance, so it is not necessary to analyze the rest of the options. The classifier that we are using is a convolutional neural network called Hyper-3D-Net Lite because it is a modification of the Hyper-3D-Net architecture that we proposed in a previous work, specifically for hyperspectral image classification problems. So in the first stage, we have 3D convolutional filters. In the second stage, we have a series of 2D separable convolutions. And in the end, notice that we are avoiding to use fully connected layers. So this network is very light in the number of floating operations and in the number of trainable parameters in comparison to other famous architectures like ResNet or AlexNet. So it can be trained really quickly. So far, we discussed about a way to find the best wavelengths from hyperspectral images, but what we really want to do is to design compact multispectral sensors instead of using full hyperspectral sensors. The main difference is that a multispectral filter can capture a wider region of the spectrum of light in comparison to a hyperspectral filter, which is very narrow. So we will use the original hyperspectral data cube and we will simulate applying multispectral filters. And here we have an example. In the case of the COCHA dataset, the bandwidth is 4.2 nanometers, but a pretty standard bandwidth for a multispectral filter is around 20 nanometers that encompasses 5 spectral bands in this case. So if we consider that this is our wavelength center, we can fit a Gaussian around it, and we consider four neighbors. So we integrate under the curve, and the resulting value represents the reflectance value of the simulated multispectral filter. In our experiments, we will report the results that we obtain using the original data and the simulated multispectral data. And let's talk about the results. First, we will use all the bands that are available for each data set. In the case of the coach dataset, we have 150 bands, and we train classifiers using 5 by 2 cross validation. And we report the average performance and the standard deviation. And we use four metrics: the overall accuracy, precision, recall, F1 score, and I'm also reporting the number of trainable parameters. So if we apply the interband redundancy analysis using a threshold of 10, we reduce the number of bands to 17. So these are the resulting classification performance. Notice that we obtain just a little drop in performance, even though we remove almost 90% of the bands. In the case of the Indian pines, it's a little bit more interesting because after reducing the total number of bands and training a classifier, you notice that the performance is a little bit better than if we use all the available bands. Even though this difference is not statistically significant, we obtain a dramatic reduction in the number of trainable parameters. Here I'm showing the results after using greedy spectral selection for the coach dataset. And we have two cases, when we select 6 bands and when we select 10 bands. As I mentioned at the beginning, we're going to try a range of values for the BIF threshold between 5 and 12. For each case, we obtain a different selection of bands. Even though they are similar, we choose the selection that gives us the best F1 score. So when we select 6 bands, the best BIF threshold is 10. And when k is equal to 10, the best threshold is 7. Something similar happens for the Indian pines dataset. Here we select only 5 bands because if we select more, we will not be able to see the difference in performances. And the best threshold in this case is 10. Next, we compare our method to other band selection methods. Hybrid is a method that uses a genetic algorithm. OCF is a clustering framework that groups all the bands according to a given criterion, and then it selects the bands with the higher ranks. Something similar happens in the first method that uses an Euclidean distance as similarity measure, and then uses local density and information entropy. PLSDA is a feature extraction method, but we adapted to be a feature selection method using the scores obtained by PLSDA, and then we select the top K original bands. In all the cases, we are using 5 by 2 cross validation, but in the first row, we report the results using the original data, and in the second row of each case, we are using the simulated multispectral data after the Gaussian transformation. So you can see that in both cases, our method obtains the best result, and this improvement is statistically significant. We use a pair t-test to verify that. You can notice as well that the difference between the results using the original data and the results using the multispectral data is small, which does not happen in the other methods. And that tells us that our method is selecting suitable filter centers. Something similar happens when we apply our method to the Indian pines dataset. In conclusion, we verified that the hyperspectral imaging systems provide detailed information about the scene, but they are very complex and expensive computationally. That's why we propose the interband redundancy analysis, which groups similar spectral bands and simplify the hyperspectral image classification problem. Our results show that the combination of the interband redundancy analysis and the greedy spectral selection method outperforms other feature selection methods. We also see that the interband redundancy analysis provides potential filter centers that are suitable for the design of multispectral sensors. And for future work, we are planning to explore implementation issues associated with developing multispectral sensors based on the designs or the bands that are recommended by these methods. So that's all, and thank you for your attention.